Web browsers, Notepad, Word, spreadsheets, PDF readers, most application processing and displaying text come with a find function that is accessible under the Ctrl+F shortcut. Finding a pattern in a text is usually referred to as pattern matching or string matching. It exists numerous algorithms and data structures to solve this problem, but today I want to focus on the one that is considered as the most efficient in usual applications, the Booyer-Moore algorithm. I will start with a naive approach, then discuss the different observations and ideas developed by Booyer-Moore. I will guide you through all the intuitions necessary to develop a fully functional Unicode-proof JavaScript implementation of the Booyer-Moore string matching algorithm. The naive approach starts by comparing the first character of the pattern with the first character of the text. If the comparison fails, the first character of the pattern is compared to the second character of the text, then to the third. The pattern is shifted to the right by one character every time, until the characters start matching. One of the first realizations to make is that if we start making the comparison from the right of the pattern, if the characters don't match, and if the character ti doesn't exist in p, then we can completely shift the pattern to its right, avoiding a lot of unnecessary checks. If the characters are matching, we keep comparing characters by character from right to left until the comparison fails or until we found the pattern. A second observation we can make is that if the characters don't match, but the character t of I exists in p, then we can shift the pattern to align its last occurrence of this letter with ti. These two observations are called the bad character rules or the bad character jump. If we keep going, we can see that we can skip a lot of unnecessary checks. If the characters are matching, we keep comparing characters by character from right to left until the comparison fails or until we found the pattern. The second main idea of the Booyer-Moore algorithm is called the good suffix rule or good suffix jump. So we are searching for a pattern in a text. Let's say that the last character of the pattern is matching. The second last one too, but not the third one. However, we know that the text matches the string AB, and AB is found 3 other times in the pattern. So we can use this knowledge to shift our pattern to align one of them with the AB of the text, but one of them has a D next to it. So we know that if we shift our pattern to this one, we'll be in the same situation and it will not match. If we look at the 2 other patterns, the letter next to them is not a D, but a C and an E. So we can shift the pattern like this, but not like that. If we shift too much, we may miss the pattern in the text. Consider the following example, where the pattern is clearly visible in the text. We start comparing from the end, the last 2 letters match, but not the third one. So if we decide to use the first occurrence of A, B in the pattern, and not the last one, we will miss the pattern in the text. But if we use the last occurrence, we can find it. If we come back to our previous situation, we shift the pattern to the last occurrence of A, B in the pattern. We start comparing from the last character. B, A, D, B, A are matching, but C isn't. But the substring A, B, D, A, B exists in the pattern, so we can shift our pattern to this position. And we can keep going, but I think you understand the idea. Before showing you the algorithm, you need to be aware that the good suffix and character roles compete with each other. If we go back to our previous example where we have the matching suffix AB, but the third character from the right doesn't match, if we replace the 0 by an E, we have this choice between shifting the pattern to the last occurrence of AB or to the last occurrence of the E. So when we have the choice, we choose the one that leads to the most important shift to skip as many unnecessary checks as possible. Now that we know the 2 main rules of the algorithm, we can start implementing it. There are multiple possible implementations. I will show you my own. I will do it in JavaScript, but it should be easy enough to convert it to any other language. You can find the full code on GitHub. The link is in the description. Let's start by defining a constant n to hold the length of the text, and another one called m for the length of the pattern. Then we call the function compute bad character role to deal with the bad character role. Usually it returns an array where indices represent all the characters in an alphabet, and the value is the position of the last occurrence of that character in the pattern, or -1 if it isn't present. But I want my code to work with Unicode characters, and if you've watched my last video about characters, you know that there are about 150,000 characters. So instead of an array, I will use a hash map. Then it will be the turn of the good suffix role that we will implement in a function, and we'll return an array containing how much we can shift the pattern when a comparison fails. For example, if the comparison fails at index 6 of the pattern, we can shift by 9. So when the good stuff is computed, we can create an index t that will help us go through the text. To do that, we use a while loop that exits once t is too large and the pattern overflows the text. Then we define the variable j to index the pattern starting from the end. Then we want to compare the pattern with the text. So we compare the character at position j in the pattern with the character at position t plus j in the text. While they are matching, we go to the next character by decrementing j. If the pattern is found in the text, j will become negative. So we want to break out of the loop once we've successfully compared all the characters in the pattern. Once we are out of the loop, it means that when comparison failed or that we found the pattern. If the pattern was found, j will be equal to -1. So I return the position of the beginning of the pattern in the text, so my code will only find the first occurrence of the pattern. But of course we could just store it in an array and continue to find all occurrences. If the pattern wasn't found, I extract the character of the text that didn't match with the pattern to use it with the bad character rule. So I check if the hash map contains this character. If it has it, then I get its last occurrence in the pattern, otherwise I take -1. If we subtract the last occurrence of this character with j, we get the value of how much we need to increase t. But the bad character rule is also competing against the good suffix rule, so we take the biggest value that will result in the biggest shift. And if after all that we were unable to find a pattern in the text, we return -1. Okay, so we'll still need to define the code for the bad character rule and the good suffix rule. Let's start with the bad character rule, which is a function taking the pattern as an argument. We start by creating a map, then go through all the characters in the pattern. The character will be the key and its position will be the value. Because we go through the pattern from left to right, if the character appears multiple times, only the last position will be stored in the final hash map. Finally, we can return the map, and that's it for the bad character rule. Now for the good stuff, the good suffix rule. The good suffix rule algorithm is fairly short, but quite tricky to understand. There's actually a variation of the Booyer-Moore algorithm called the Booyer-Moore algorithm that completely ignores the good suffix rule. Don't worry, I made it simple to understand. It's gonna be alright. So we have a pattern. We are trying to find it in a text. Let's say the text matches the pattern until it doesn't. So we would like to know if this pattern exists somewhere else in the pattern. If it doesn't, well, we know that we can completely shift our pattern, but if the pattern exists, it can be in the middle of the pattern, or it can be a prefix of the pattern. The pattern can also exist multiple times, but as we saw in the example, we only care about the last occurrence of the pattern. But that's if we can find the full matching substring inside the pattern. What's also possible is that we can find a prefix of p that is also a suffix of the matching substring. So in this case, we will still be able to shift the pattern, but we will only use this suffix. You would think that that's a lot of cases to consider, but what if I told you that these are really just variations of the same case? Which is about finding the longest proper suffix, which is also a proper prefix. A proper prefix that is also a proper suffix is called a border. When the matching suffix is a prefix of p, we clearly have borders. When the pattern is in the middle of p, then if we remove the beginning of p, we have borders. Even when we can't find the pattern of a suffix of the pattern, we are still looking for a border, but we can't find any. So yes, all of these cases are about finding a border, a prefix that is also a suffix. Okay, but how do we actually find this? We need to make a few observations. The first one is that if the border exists, the left border can be anywhere in P. It can even overlap the right border. But we know that the right border is always a suffix of P. So in order to find the left border, we will consider all suffixes of P, starting from the right. The second observation is the following. Imagine that you have found the longest border of this substring of P. Then if we are looking for the border of the next bigger suffix of P, if we compare the character on the left of the left border with the character on the left of the right border, then if they are equal, we found the longest border of this substring. But if they are different, then the right border cannot start here, but it can start at the position on its right. So the border can start in the blue area, which is the previous longest border. I want you to realize something about this previous border. It's the same on both sides. This border is a suffix of P. This substring can also have borders, and the leftmost character of this substring is next to that red pink border. This pink border is also a suffix of P. So if the character on the left of this right border is equal to the leftmost character, then we found the longest border of this substring of P. But if they were not equal, well, we end up in the same situation as previously. So we repeat the operation until we have no more borders or are running out of characters. Let's summarize what we learned. 1. We are going to look for borders from right to left, and we will use the letter I as an index. And 2, we are going to use the previously found borders to find the next ones. Now that we have an intuition on how to find borders, let's start to think how we can implement it. Let's consider the rule before the behavior at the base case. Let's say that we know that the blue area is the border of P of I to M. We want to find the borders of the substring P of I minus 1 to M. So we compare P of I minus 1 with P of J minus 1. If they are different, we want to find the borders of the previous border, so we can compare P of I minus 1 with the character on the left of the right border. And we want this character to be P of J minus 1, meaning that the character on its right is P of J, which is also the beginning position of the right border. So in order to change the value of J to the new one, we are going to need to store for each J the position of the beginning of the right border. And we are going to do that with an array called border. But how do we fill it? Let's say that we know that the blue area is the border of the suffix of P starting at I. It means that the border of I must contain the position of the beginning of the right border, which is J. Now, if we look at the border starting at index I minus 1, if P of I minus 1 is equal to P of J minus 1, then the border of I minus 1 is J minus 1. And we can repeat the operation as long as the characters are equals. In other words, while P of I minus 1 is equal to P of J minus 1, then the border of I minus 1 is J minus 1. And then we decrement I and J to test the next characters. Or we can rewrite it to first decrement I and J and set border of I as J. Also, we want to make sure to stop before I becomes negative. So we add a condition in the loop. But that was only the easy, obvious case. When the characters P of I minus 1 and P of J minus 1 are different, we are interested in the right border of the right border of I. Because border of I is J, we want to get the value of border of J, which is the position of the beginning of the pink border, and we use this value to update the value of J. And we repeat this operation until P of I minus 1 and P of J minus 1 are equal, or that we are running out of borders. So while pattern of I minus 1 and pattern of J minus 1 are different, J takes the value of border of J. When the characters are finally equal, then we found the border of I minus 1. Okay, but here we are missing a condition to break out of the loop when there's no more borders. Let's take the following pattern. If we take a look at our code, we want J minus 1 to be able to reach the last character of the pattern, which means that J must take the value of M or 8 in this example. And because j can take the value of 8, we should be able to index the array borders with 8. It means that our border array should have m+1 cells, or here 9 cells. And if we enter the loop, we are going to read this value. If we read this value, it means that we reached the end of the pattern. There is no more letters to read. So we are going to give it the value m+1 to have our j-1 outside of the pattern. But because pattern of j-1 when j is equal to m+1 doesn't exist, we are going to exit the loop when j is greater than m. Now that we've covered both cases, it's time to merge them together. To do that, we need to realize that we have two while loops with opposite conditions. If we delete the condition in the first while, we consider that p of i-1 is always equal to p of j-1, which is not true. But we can use our second while loop to deal with that case. And if we look at the line after the second while, it's similar to the 3 lines inside the while. So if we put the second while inside the first one, the merge is complete. We now just need to initialize the various variables. Let's start by defining the constant m as the length of the pattern. As we just saw, we want our array borders to be of size m+1, and we want the last cell of this array to contain m+1. But because our algorithm computes borders of I equal j, we can initialize I to m and j to m+1 and set borders of I to be equal to j. And finally, we got our algorithm to find borders. Okay, but why are we doing all this already? Yeah, shifting. You know, at one point, we'll be in our text at index t, and we will compare our pattern with the text. Everything is matching until j-1. And at this point, we would like to know if we can find the matching suffix in p, and if it exists, we'd like to know its position, so we can shift the pattern to align with the text. Or in other words, we want to know by how much we want to increase the value of t. Of course, we want the character on the left of this new location to be different than the character at position j-1. This diagram should be oddly familiar, right? What about now? If I add an I and i-1, yeah, it's the same situation when we were looking for borders. So if we know that the border of I is j, then if p of i-1 is different than p of j-1, then we want our character at position i-1 to be aligned with the character at position t plus j-1. And this distance is j-i. So we are going to build an array called shift to know that when we fail the comparison at position j-1, we will shift the pattern by j-i. If we go back to our code to find borders, we are going to create the array shift of size m, and we will fill it with zeros. When we detect the end of a border, when the characters at position i-1 and j-1 are different, we will store j-i. But we need to be a bit careful here, because we are setting shift of j-1, so j-1 can be negative. So we add a condition to make sure it's superior or equal to 0. And because we are probably going to visit the same position multiple times, we don't want to erase our previous work, because we only care about the last occurrence. So we'll only set the value of shift if it is equal to 0. And that's it. That's it. We are done? Nah, not yet. Remember when I told you that these are really just variations of the same case? Well, it's true, but when we are looking for how much we need to shift the pattern, we need to consider two cases. The one where the matched pattern can be fully found inside of p and is not a prefix of p, and the second case where a prefix of p is a suffix of the matched pattern, or is the matched pattern. The algorithm we wrote only finds the shift of the first case, so we still need to find the shift for the second case. Let's consider the following pattern. After running our code, we get the following borders and shift arrays. You can see that the shift array is mostly filled with zeros. We are going to change that. Imagine that we are trying to find the pattern in a text. Let's say that all the characters of the pattern but one matches the text. the first character of the pattern doesn't match. We want to know by how much we can shift. If you look at this character, it's part of a border, and this border was found in the text previously. So we can shift T, so the beginning of the pattern aligns with this part of the text. We need to shift T by 6 characters to the right, which is given by the position of the border. Now, if instead of failing at the last character, the comparison failed on the character before it, well, the pattern still matches the right border starting at position 6, so we can also shift by 6. This is true for all the characters up to the beginning of this border. When we hit the border, this time we can't keep shifting by 6, because if we do, the comparison will be the same and will fail. So instead, we need to look for the longest border of this border, because the border starting at position 6 has a left border, then the borders of the right border are the same as the one of the left border. So we know that the beginning of the right border is a prefix of the pattern and was found in the text. So we can shift the pattern to this position. So for this position, we can shift by 9, which corresponds to the beginning position of that border. Now, if we continue, we are in a similar position as previously, where AB is still a prefix and suffix of P and was found in the text. So we can shift by 9. Now for the next position, we already computed the shift when we were finding borders. So we already know that we can shift by 3. For the next one, we are reaching the borders, so we can't shift by 9 anymore. But if we take the border of this substring, which is 11, we know that we can shift the pattern by 11. Now for the last character, we already computed the shift, which is 1. The algorithm is pretty straightforward. We start by initializing a variable b to be the position of the first border. Then we are going to loop through the shift array, and if the shift is 0, we are setting it to the position of the border. We keep doing that until we reach the border. When we reach it, we set the value of b to its border, which will set the value of shift to be 9. If we keep going, we are going to fill the shift array entirely. So here's the pattern. If you want to verify, you can pause the video. If we take our code that finds borders and add the code to complete the shift array to it, we get the good suffix role algorithm. We just need to return the shift and that's it. We are finally done with it. Our algorithm is complete and can work. Well, actually, we can make it better. There's an optimization we can make, but I don't want to cover it. But there's something I want to do. I want my code to work with Unicode characters. And if you've watched my previous video about characters, you know that some abstract characters can have multiple Unicode representations. And comparing them with the triple equal sign returns false. So I would like to avoid situations where I'm looking for pretty much the same pattern, but I'm not finding it because I'm using the wrong representation. To fix that, I will normalize the strings with the normalize method. And now it works as expected. If you reached this part of this video, holy shots. This is the end of the video. I hope it was clear enough, and if it was helpful, you can consider liking the video and subscribing. Could help me. It would be pretty nice. And if you're an absolute chat lord, you can also share the video with your friends. So goodbye, man. Have a good day. This is the end of the video. Have a good day. And thank you for watching, and enjoy, and have a good life. And I hope you get everything you want in life, and you're healthy, you feel good, and you're happy, and you successfully reach your goals, and you're doing good. So whatever. Goodbye.